In this review, we're going to consider all type of series test in one short video. So you can see that we're going to go through like all major series test, including we're going to start with geometric series, p series, nth term test, and then direct comparison, limit comparison, and then absolute convergence test, integral test, and then also alternating series test, and then ratio test and the root test. So let's call it series test, series reviews, all in one, all in one. So we will go through every like pretty much everything that we learn. So let's recall few things. So there are few major things that we need to know. So recall. The first one is the dominating terms. Dominating terms decide the convergence and divergence. That's very important. Dominating terms decide the convergence and the divergence. So that's one of the very important thing. The second one is the geometric series. Geometric series. Geometric series is any series that you can write in this form. So you can start with any index or any numbers, or let's put 0 here to infinity. A, R, N. So this is N or N minus 1 depending on how you want to write it. So this A over 1 minus R. So this gonna converge when absolute value R are less than 1. And then diverges when the absolute value of R greater than or equal to 1. So how to remember this? We're gonna remember in the number line. So what's gonna happen if it is in between 1 and negative 1? If in between 1 and negative 1, it's gonna converge. So the outside is gonna diverge. Okay, that's the danger. So red light. So diverge outside. Perfect. And then so the next important one is the P series test. P series. So what's a P series? We have sigma n going from 1 to infinity, 1 over n to the p. So it is in the denominator. There are two things. It's going to converge if p greater than 1. Remember, it is opposite to the geometric series, and the diverge if p less than or equal to 1. So it's opposite, pretty much, not all. So let's draw this again. So what's going to happen here? So it is 1 is there. So what it says that is a more than 1. So this side is going to converge, and everywhere else is going to diverge. So slightly different. So if you draw the interval, it is from 1 to infinity, is going to converge. Negative infinity all the way to 1 is going to diverge, including 1. Okay, so those two are very important because we're going to use this a lot. And then the other point is, if you want to find the sum of a series, there are only two ways to do it. Need the sum of a series. So we need the sum of a series. So need the sum of a series, the actual sum. The one major method is the geometric series. Geometric series. We know that it is going to be 1 over 1 minus r. A is the first term. So find the first term, plug in the first index value, whatever the index value. It can be 0, it can be 5, it can be 1000, whatever. The next one, so that's the first method. The second method is the telescoping series. Telescoping series. So those are the only two methods that we can find the series. And then actually we also learn something from the Taylor series. Taylor series also can be used to find the sum. So Taylor or Maclaurin series. Because you can represent this as a function, representing it as a non-function, non-series. So representing as a non-series, so log or something like that, then you can do that. So that's the another way to do it. Taylor Maclaurin series. Okay, so the most two common one are geometric and the telescoping series techniques. Okay, so let's go through each one one by one. So let's start with the first one. So it is the so let's look at this example. So it is sigma n going from 1 to infinity, 1 over n e to the pi. Okay, let's try it again. So so it is n e to the pi. So what do you know about e to the pi ratio? We know that e to the pi is roughly 2.718. Pi is 3.145, so that means less than 1. So then you can see it's less than, so diverges by the p series test. Diverges by p series test, because p is less than 1. Good, done. Okay, so that means the series has to be diverged. Okay, and the next important one, so I'm going to go in the kind of order. So you can see that this is like it looks like n to the p, so that's why we go with the p series test. So now you may wonder why I picked that test, because it looks like p series. So let's go. So the next important one that we go in order is the, just to save time. Okay, let's write it first. So it is, let's say, n squared minus 5n plus 1. It can be like any complicated one. And let's say 9n to the 4th power plus 3. Let's put a square root as well. Okay, something like that. So it's an algebraic expression. So what you're trying to do, you can look at the dominating terms. When you look at the dominating terms, it almost look like, you can see n to the 4th square root, that means n squared get cancelled, so that means you're going to get 1/3 as the limit. So the next one is, you look at the dominating terms and try to kind of identify what the limit look like. So the limit decides what's going to happen. You can see that in this case the limit going to look like 1/3. Okay, so that means we're going to use the nth term test. So that's kind of the second one. We look at the nth term and see what it looks like. Okay, so that's the second important method that we try to do. We look at the limit. So you can see, you're going to see the limit. N goes to infinity. N squared minus 5n plus 1 over 9n fourth plus 3. What is important is only the dominating terms. So let's take the limit of the dominating terms. So it is n squared over 9n fourth square root. You can see squared fourth get cancelled because it's squared, so you simply end up getting 1/3, which is not equal to 0. So that means so diverge by the nth term test. Okay. Diverge by the nth term test. The next example. So let's do geometric one. So let's do this one. So sigma n going from 1 to infinity, 2 to the n minus 1 to the n, 3n, something like that. Okay, so now if you get a series like that, you can again look at the n term. So you can see, once you look at the n term, see that n appears in the top and bottom. So these two and that one, you see. So it says that it looks like geometric because you can write this as something to the n power. So that's why, so because of that, we're gonna decide, we're gonna use the geometric series test, okay, because it looks like geometric. So sigma n going from 1 to infinity. So let's split this into 2. So it is 2 to the 3n minus, and then you can write this one as sigma n going from 1 to infinity negative 1/3 to the n. I hope this step is clear now. You're going to pull out only the terms with n, okay, and combine them. You pull out terms with n and combine them into one. The negative sign is the negative sign in the middle, okay. So good. Now what we can do, we're going to look at the rest of the things. So you can see r, in this case r is 2/3. So once you take the absolute value, it is less than 1, so it's going to converge. The other one is r equal negative 1/3. Once you look at the absolute value, which is 1/3, which is less than 1, so it's going to converge again. If at least one of them diverge, the whole series diverge. So you cannot talk about any sum because infinity or does not exist. Yeah, so what do you want to look at? If at least one of them diverge, the whole series diverge. But in this case, both converge, so that means you can find the sum. So we use the sum formula, a over 1 minus r formula. So a is the first term. Plug in the first index. In this case, the first index is 1. So we're going to plug in 1. If it is 2, plug in 2. But in this case, 1. So we're going to plug in 1. So that means 1 means that we're going to plug in 1 to the power. So it is 2/3 in this case. So you get 2/3 as the first term from the first series, divided by 1 minus r is 2/3 again, and then minus. In the next one, the first term is 1/3, negative 1/3, divided by 1 minus 1/3. See, there are two minus sign here. Okay, now we can simplify this. So it is 2/3. 1 minus 2/3 is 1/3 minus. You can say minus plus if you want, like that. So it's easy. So at the bottom, minus plus, so it becomes 4/3. Now you can simplify these two together. So you can see 3 you can cancel. You know that you can simplify denominators and the numerators separately. So I'm going to cancel the 3 from the denominators. And the same argument works here, 3 from the denominator. So you can simplify denominators and numerators separately. And then what's going to happen is you're going to get 2 over 1, that's 2, plus 1 over 4, 1/4. This is easy. Take the common denominator. So it's you multiply these two and then add that. Okay, that's what happens. So multiply and add. So that means you're going to get 8, 9. So 9/4. Okay, so 9/4 is the sum. That's the sum of the series. So this is only one way to find the sum. Good. So let's do now let's go to the next important one, what we call the telescoping series problem, because that's another one to find the sum. So example number 4. So let's look at this series. So sigma n going from 1 to infinity. Again, you can start with any number you like. Okay, so 4 over n plus 1, n plus 3. Okay, something like that. N plus 1, n plus 3. So if you see this, you can see that these are two consecutive odd numbers. Okay, so consecutive odd numbers. So consecutive odd. So if I just ask whether this is going to converge or diverge, you don't want to go this far. Look at only the dominating terms. Okay, in this case, you only need to look at 4 over n squared. 4 over n squared, that's almost looks like a p series. So p equal 2, so this has to converge. That we know. But here, maybe they are asking find the sum as well. Okay, so if you need to find the sum, it's definitely geometric or telescoping, but this is telescoping. Okay, so so you can see you can use the telescoping series argument. So what you're going to do, so since it's consecutive odd terms, you're going to try telescoping. So we can write this one as 4 over n plus 1 n plus 3 right, identical to a over n plus 1 plus b over n plus 3, and then if you multiply by the denominators, you're going to get 4 identical to a n plus 3 plus b n plus 1. Now what we can do, we're gonna do a smart substitution here. We're gonna substitute n equal -1. Once you do that, the other second term get cancelled, so you get 4 equal a times 2. This says that a equal 2, and then also we're gonna do another smart substitution. You're gonna do n equal the other one, -3. So it's 4 equal this is 0 plus b times -2. This says that b equal -2. Okay, we find the two numbers. Now what we can do, we're gonna substitute those two numbers here. So that means this is gonna be a equal to, so 2 over n plus 1 minus 2 over n plus 3. So we're done. Now what we can do, we're gonna consider first n terms. Okay, so consider first n terms. So we try to find the pattern and then send n to infinity. So let's plug in. So we start with the first index. So if you plug in the first index, and first index is 1, so you're going to get 2 over 2 minus 2 over 3. That's the first term looks like, plus the second term look like, plug in n equal 2, so 2 over 3 minus 2 over 4, that's the second term. And if you look at the third term, it is 2 over 4 minus 2 over 5, like that. So your n term looks like n over n plus 1 minus, or not n, 2 over n plus 2 over n plus 1 minus 2 over n plus 3. Yeah, actually I think I made a slight mistake here. So that's the wrong number I plug in here. Good. Okay, good. So when you plug in the numbers, you're gonna get so when n equal 1, when you plug n equal 1, you get 2 and 4 here, and then when you plug in n equal 2, you're gonna get 3 and 5, and then when you plug in n equal 3, you're gonna get 4 and 6, like that. Now let's see what's gonna happen. So when you look at this sum, you're gonna see some terms get cancelled. Is that right? So so you can see that it's a little far away, but you can see that it's going to start cancelling. So you're going to see that this term get cancels with that term. You see that, because it should appear sometime, and then when you write when you see more and more terms, and then you can see that it's going to start cancelling, and then you can see if I had written the next term, so you can see this term get cancelled with the first one of the next one. So all these cancels, and at the end you only end up with these two terms, this and that. Okay, so now you can see that when n goes to infinity, this goes to 0. When it goes to infinity, this goes to 0. That means your series simply end up with two numbers. So what's going to happen? The sum going to end up with these two numbers. What two numbers? 2 2 and 2/3. Okay, so you can see that this gonna end up with 2 2 plus 2/3. Those are only two numbers that you end up getting, and then take the common denominator, that is 6. So you cross multiply. So you multiply these two and add them. So you multiply this with that and this with that and add them. So that's how you get the number. So what's the number you're gonna get? You're gonna get 6 plus 4, so 10 over 6. Okay, this is 5 over 3. So that's the sum is gonna converge to. yeah, so it is 5/3. 5/3 is the sum. So you can see as n goes to infinity, all the other terms get cancelled, so you only end up getting the first terms whatever are left from this sum. So the sum is 5/3. So this is what we call the telescoping, they're cancelling each other. Okay, so look at the first few terms, how it looks like. Good. So that's telescoping, and then what's gonna happen is so let's do the direct comparison test problem. So the next one is so let's look at this. So this is example number 5. This example number 5. Let's look at this problem. N going from 1 to infinity, ln n over n, something like that. So if you look at this problem, there are two things actually we can think of. This problem you can, because you can see this also easy to integrate. So one thing is, another way to do this problem is the integral test. But what we try to do is you're gonna see whether you can compare this with something easy. But if you think of the graph of natural log, you can see that the graph looks like that. So that means it's gonna reach 1 at some point, but you know that it's gonna reach at e is roughly 2.718, so it's like little less than 3. So that means if it is bigger than 3, the ln is greater than 1. So that means you notice this. You notice that ln n over n is bigger than 1 over n if n greater than or equal to 3. But you know that you can ignore the first million terms of a series. That still doesn't change the convergence or divergence. It change the sum, of course, but it doesn't change the convergence or divergence. So, but this is true. But we know that. But sigma 1 over n diverges. So we can say diverging p series. Diverging p series with, you need to say the p value, okay? P equal 1, so that's less than or equal to 1. That's what the test is. So therefore by the direct comparison test, the original series gonna diverge. I'm gonna do one typical problem also, but I normally do only one problem in this one, but let's do it one more, because this is also very typical for this kind of problems. So how about this one, sigma n going from 1 to infinity, 4 over n3 plus 2 maybe, okay, something like that, n cube plus 3. But you can see that one very important observation. So when you see that, look at the dominating terms. So the dominating terms looks like this, okay? So it is almost a p series. So that's the almost a p series. So you try to compare with the p series. So what we're gonna do, we're gonna write this one. We're gonna see 4 over, so we can see 4 over n3 plus 2 is less than or equal 4 over n4, right? Because if you add something to the denominator, it's gonna go smaller, so it's n3. So this is true, but the other side gonna create a p series, okay? But you can see that sigma n going from 1 to infinity, 4 over n3, you can actually ignore this 4, because you can just pull out that. It's not really necessary, but you can do it if you want, okay? So is a converging p series. Converging p series, p equal 3, which is more than 1, so converge, okay? So by the direct comparison test, the original series converge. Very good. So let's look at next example. So the next one is from, so let's look at it and see what it looks like. So let's do this one. Sigma n going from 1 to infinity, n squared over 5n7 3n minus 4, something like that. So you can see that so I don't want to start with n equal 1 here, because if you start with n equal 1, if you plug in 1, what's going to happen? You get negative. So let's start with n equal 2. Okay, so you can see that n equal 1 doesn't work here, because it's not it doesn't exist. Okay, so what do you do when you get a series? Always look at the dominating terms. If you look at the dominating terms, that's one of the dominating term on the numerator, and that's the dominating term in the denominator. So just look at them, and once you look at them, it looks like p series. Okay, it looks like p series. So so what we're trying to do is you can see that this is very difficult to use the direct comparison, because if you try to use the direct comparison, you have to consider all type of why those 3n is in the bottom. So because you need to have the right inequality. So for that, we are not going to go for the direct comparison for this problem. We're going to go for the limit comparison, because then you can ignore most of the other terms. So that's the trick. We try to use the limit comparison for this problem. Okay, so we only need the dominating term. So let's look at the series with the dominator. So we're going to compare this with the series which has only the dominating terms. That means n squared from the numerator, and from the bottom 5n to the 7 square root. If you simplify this, you're going to get n squared over, so I'm going to, let's write it properly. So you're going to say equal to what series? This equal to the series with you're going to get, so what will happen? It's n squared over square root 5. If you take the square root of that, it's becomes 7/2. 7/2 means 3.5. So if you simplify this, you simply end up getting 1 over square root 5 is a number, n to the 1.5. Okay, so that means 1.5 is more than 1. So the series has to converge. So that means this side is simply become a converging p series with p equal 1.5, which is more than 1. So by the, what do you do? A limit comparison. Let's look at the limit now. So we're going to look at the limit. So I'm going to consider the first one is an. So I'm going to say this is an, and that is bn. So if you go with an over bn, you can see the way we selected this, the way we selected this, because you take all the dominating terms. Okay, all the dominating terms, that means going to be 1. Okay, so that's, so this always happen if you do not ignore anything. You have to consider all the dominating terms. So it's be 1. So this is not equal to 0. So then by the limit comparison test, the original series, that means an converges, because the other one converge. Okay, so very easy. You can see it's very easy. So limit comparison test is one of the favorite. Okay, one of the favorite. Good. So let's go to number 7. How about this series? So let's do this one. Example number 7. So if you look at sigma n going from 1 to infinity, n e negative n squared. So if you see like these kind of expressions, one thing that you notice is it's easy to integrate. You see that? It's easy to integrate. If easy to integrate, use the integrating test. Try integrating test. Okay, so if it is easy to integrate, use the integrating test. That's the kind of argument that we do. So let's look at the corresponding function. So the corresponding function is x e to the negative x squared. This you can write as x over e to the x squared. So but now you consider the three properties. So this is positive, and then this is continuous because e never becomes 0, and then also decreasing. How do you know this is decreasing? So there's an easy way to see that. You can see that you're going to see x and ex squared. Ex squared grows much faster, so that means going to decrease. Okay, so ex squared grows faster. So that's one way, or use derivatives. Okay, so you can use any other argument like that, but if you just mention that, that will be enough. So let's try to and this is an improper integral, so we will convert the problem to the improper integral. So it is 1 to the infinity x e to the negative x squared dx, and by the definition this is the limit b goes to infinity 1 to the b x e to the negative x squared dx. This is one of the easy integral because the derivative of the exponential part is negative 2x, but x is there, so we can manipulate the rest. So what we're going to do, we can write this one as the limit b goes to infinity. Negative 2 is missing, so you're going to divide by negative 2, and then we're going to multiply inside by negative 2. So that's the trick, and then we can use the 4 formula trick. So by the 4 formulas, so by the 4 formula trick, so you can see that this is simply e to the negative x squared, and then we can evaluate it at, oh actually I put infinity here, so let's change this to b. We're going to put b at 1, and you can see that this is easy to integrate. Just plug in the numbers there. So it's negative 1/2, the limit b goes to infinity. So if you plug in b, you're going to get e to the negative b squared minus e to the minus 1. That's what you get. And we know that when you look at the exponential graph looks like that. That means when it goes to infinity, this goes to 0. So that term goes to 0. So that means you simply end up getting what do you get when you plug in that? So you're going to get 1 over 2e, which converge is finite. Okay, less than infinity is finite, so that means converge. So that means the integral converge. So by the integral test, you need to write this. Okay, integral test, the series converge. Perfect. Okay, so so let's go to another one. Number 8. So I'm going to go through like all types. So let's look at this one. So let's see sigma n going from 2 to infinity, cosine n squared over n3 minus 1 square root, something complicated like this. So if you try to just apply the techniques that we want to use, you see that the top is a change in the sign, because the cosine changes sign, so it's go through positive and negative values, and most of our series test does not work. For example, you can use direct comparison or limit comparison, because for those two the terms has to be positive. So what we're going to do, we're going to consider the absolute series. So when you see sine, cosine, or if the sign of the terms changes, consider the absolute series, because if the absolute series converge, then we have a theorem which says that the absolute convergence test says that the original series has to converge. So what we do, we instead of this, we're going to look at the absolute series. So cosine n squared over n3 minus 1 square root. Okay, so and then if you do that, so you can see, so there are certain things that we can see, because if you look at the absolute terms, because we know that the cosine is always in between negative 1 and 1, so this part has to be less than or equal 1 over n3 minus 1. I don't write the absolute sign anymore because this is positive. Okay, we start with 2. You can start with 1 because then you get 0. So this is and then you can see that this is almost looks like 1 over n to the 1/5 because you look at the dominating terms. So it's a p series. Okay, so then we can say so the absolute series in converges since it's a p series with p equal 1.5, which is more than 1. Okay, so the absolute series converge. So therefore, by the absolute convergence test, the original series converges. Good. So let's go to the next example. Example number 9. How about this one? Sigma n going from 1 to infinity, -1 n over square root n. Okay, so one thing that you notice is, you see this is the sign changes. Okay, so you notice that this is a alternating series. So if you see that's an alternating series, and then you can see that then you can use the alternating series test because that's the best choice for this one. So let's try to consider the two conditions. So in this case, the first condition, we know that the bn, which is 1 over square root n, we ignore the sign. That's how we get the bn. You know that goes to 0 as n goes to infinity. The first one is passed. The second one is bn, which is 1 over square root n. It's very clear that this is decreasing because the dominant term is in the numerator. So it is decreasing. Because n in the denominator. So that's the reason. Okay, that's grow faster. Okay, so by you can say by the alternating series test, the original series converge. Very easy. So it takes like 1 or 2 minutes. And then let's do the last two. So how about this problem? So I'm going to give you the so it is example number 10. So sigma n going from 1 to infinity, -1 to the n, 3n over factorial n. Now there's a secret here. The secret is you're going to see like some powers to n, like e to the n, factorial, like n to the n stuff. This like maybe we can just a little wait for that. If you see like this kind of term, like 3 to the n, e to the n factorial, we're going to use the ratio test. So that's the secret, because it's going to make those calculations much easier. And then if you just see like some expression like n plus 1 log n, we are not going to use the ratio test for that. It's not going to work. Okay, so let's try it now. So what we can do, we can look at the ratio. So n plus 1 over n, absolute value, don't forget that. So it is -1 n plus 1, 3 n plus 1 over n plus 1 factorial, and it's a division upside down. So factorial n, -1 to the n, 3 to the n, absolute value. Now what's going to happen, you can see that this and that get cancelled because the absolute value of those are 1, and then 3n cancel with 3n, and one of the factorial n get cancelled. So you only end up getting what do you get, because you can expand this one as n plus 1 times factorial n. So factorial get cancelled, so you only end up getting one of the 3's and n plus 1. This one goes to 0 as n goes to infinity because the top is fixed. Okay, so that's it. So then you can see that by the ratio test, the original series converge. Very simple. Okay. And then the last example is this one. So this example number 11. Example number 11. So this one, sigma n going from 1 to infinity, 3n minus 4 over, let's say, 5n plus 7 to the nth power, like that. So one of the important thing again here, this n, see that power, says that try the root test most of the time. So not always. So try the root test. That n tells you that the root test. Okay, n squared, like these kind of terms, we definitely go for root test. Okay, like n to the n, like that. So some n powers. Okay. So so let's finish the job. So what we will do, we normally take the absolute value, the nth root of the absolute value. That's what we try to do. So let's do that here. So it is 3n minus 4 over 5n minus 7 n power nth root. So if you have n power nth root, you can see that this and that get cancelled. So you simply end up getting 3n over 4, 5n over 7, which goes to the dominating terms. So dominating terms are 3n and 5n. Once you divide the two, you end up getting 3/5, which is less than 1. So that means converge. Okay. So by the root test, the original series get a converge. Okay. I'm just gonna do, so it's over. I'm gonna just do one bonus problem. How about this one? So let's say sigma n going from 1 to infinity, n minus 4 over n to the n. We definitely know that we have to use the root test for this problem because the n term. So let's try to use that. So if you use the root test, what's gonna happen here? So a n absolute value nth root. So you're gonna get the n of 4 n to the 1 over n. So the outer one get cancelled. So this get cancelled. So you end up getting n minus 4 over n to the n power. Then what we can do, we can write as this one as 1 minus 4 over n to the n. Then we know that this is one of the limits. So when n goes to infinity, this is going to go e to the this number. What number? Negative 4. So it's going to go to e to the negative 4, which is 1 over e to the 4, which is less than 1. So the series converge. So by the root test, series converge. Okay. So if you need more details, you can find them this in the other reviews or the detailed lecture notes. Okay. So thank you so much.